Did we go over this light section at all?
Mm-mm.
You can start.
Remember you forgot about that one part, you had to go through all of it again?
Oh, the periodic trends, the electronegativity.
Yeah.
Okay.
We have to go through all of that. So I think it's good.
How could we did the force?
So we'll start with that. That page is the one. We did Lewis stuff.
It's almost good. Yeah, it's over 33,000
Will you give us a practice amount for this next test like you did for the
We're talking about there's another SI teacher.
Chris?
Another one? Because I can come for Tuesday.
Well, there's math that comes here at 2 o'clock, right before class, and then there's Kristen who does hers at other times. I'm not sure when.
Okay. Because I can't come to that.
I think it's 6 or 7, like tonight and Monday.
Okay.
I was just wondering
Yeah,
if she's on the same, at the same pace.
Yeah. Because she's officially the SI for the Tuesday, Thursday class, which is really right neck and neck with news. Except I was going to say we're a little off kilter. I'm a little off kilter because of the Labor Day thing, so things are a little awkward right here. But other than that,
So like these 3
we're doing this
pages.
page today.
About
This
this
was
page.
already done. That's when we did cations and configurations. So yeah, we did that.
And then that's part of the same thing.
And it's this page. The definitions are correct, but the exceptions are incorrect.
Okay. Okay.
So all I'm throwing out is that's part on exceptions.
Okay. So will this be on the test?
It will.
Okay.
Did any of your lab instructors demonstrate the Rubens tube thing for you? It's that big metal thing up high on the shelf behind where the projector screen is. You've seen it, Matt, right?
It's really awesome.
Ask for it.
Isn't it we outside your room?
We had it out there. Yeah, they wouldn't let us light it out there. But yes, we had it out there. It is. It's really cool. Ask your lab instructors. Maybe they'll get it down and demonstrate it. But what we're going to go over today is this page on light, which is material on your next exam. After that, and I've made copies, we're going to have to move with, for time reasons, material reasons, we're going to go a little bit into what would be considered exam 3 material, which is not going to be on your next exam, but it's in the exam 3 study pack, and I went ahead and copied the pages that we'll be working on today, because I know you probably don't have that yet. But it's just the first couple of pages for that, and I'll give you that when we get through with this light section. But the thing about light is one of many forms of energy. And the reason we've got light in the context here of doing electron configurations is that everything we know about that layered electron structure comes from interaction with light. Either the electrons absorb the light or they emit the light, but it has something to do with light and electrons. And just like with bonding, when we said that the protons and the neutrons that make up your nucleus, when this atom meets this atom, it's the electrons that make contact. And then we modified that so it's only the external electrons. But the point is, it's the electrons that do the bonding. Whether it's covalent or ionic or metallic, it's the electrons. Well, it's the electrons that interact with the light too. And so that's where all this stuff about configuration and quantum numbers comes from. The kind of energy that's light interacts with these electrons. So we got some properties to define, first of all, wavelength and frequency. Wavelength is an actual physical length. You could measure it in inches and feet if you want to. It's generally not, but you could because it is an actual physical distance. And it's defined as the distance of separation between one wave and the next. Greek letter lambda is the symbol that's used for wavelength. And it's generally going to be in meters or some variation on meters, like nanometers that you did with the light absorption experiment. And let's call this wave A and wave B. Which one has the larger wavelength? Apparently A, right? Larger distance of separation. The other factor is frequency, and this is Greek letter nu. And frequency is like a flow rate. It's how many waves go by per time. So just for pretend, if we say that this represents a 1 second time interval, then the top one, I guess, would have a wavelength of 4, and the other one would be something higher than 4, right? B would have the larger frequency. And so frequency and wavelength are inversely related. If the waves are coming in rapid succession, then there's not going to be much separation, correct? So they're inversely related. In particular, they're inversely related through this equation, where c is the speed of light. If frequency goes up, wavelength goes down, or vice versa, but the product is always equal to the speed of light. The speed of light, 3.00 times 10 to the 8th meters per second. That equation, c equals lambda times nu, that equation you need to know. But the value for c will be a given constant. You don't need to memorize the speed of light. But you need to know that formula. Question about their relationship. All right. Now there is another way of looking at light, rather than looking at it in terms of waves. But the term photon is looking at light as if it were a particle as opposed to a wave pattern. And so, for no particular reason, still sticking with A and B, if light source A is giving off a stream of photons, and so is light source B, and here's some object that we're shining that light onto. Each little particle of light, that's a photon. And even though we're talking about light in a particle sense, we still do the math based on waves. So whereas before we defined wavelength as the distance of separation between one wave and the next, you could think of wavelength as the distance of separation between one photon and the next. So B is pumping out photons in rapid succession. That's a short wavelength. That's a short gap between one and the next. So B has the shorter wavelength, higher frequency, correct? And the same equation still applies. It's just a different analogy for looking at it physically. It's still the same mathematics. But what that analogy kind of helps you with conceptually, that this one is not so easy, is the relationship to energy. Because if this is the object that we're pinging with these photons, which one is going to be pinging that object more times per second? B. And each little ping carries a certain amount of energy, correct? So light source B would be imparting more energy onto that object per time, right? Energy is proportional to frequency. High frequency means high energy. And the equation for that is this, or H is a constant. Units on the constant are joules times seconds. Not joules per second, but joules times seconds. You calculate energy based on the frequency by multiplying by this constant. The equation you need to memorize, the value for H will be given. Question about the relationships between frequency, wavelength, and energy before we start putting numbers to it. Right. Let's put numbers to it. Problem number 1. Work this on your own, but with one tip here. Please notice that what you're given as your starting number is micrometers. Since the units on C are ordinary meters, you can't plug 455 into your equation as being your wavelength. That 455 is micrometers. You've got to convert it into regular meters before you can plug it into this equation. So you got a little bit of unit conversion to do before you can jump into your speed of light formula. Convert micrometers to ordinary meters and then plug into this equation. See what you get. The top of the board has got your unit conversion. The lower part has your speed of light formula after you've made your distance units match. And then it's just division from it. You should be getting 6.59 times 10 to the 11th or something very close to that. And the units are per second. Formally, the units come out with just the unit being seconds in the denominator, so that's per second. But you can think of that as waves per second or photons per second. That's your frequency. Question about getting that? Two biggest problems before we work the rest of these other examples here. The two biggest difficulties people have with light calculations is one, they don't memorize these two equations. And then you're kind of doomed because you don't know what to do with your numbers. And second, they don't review their metric prefixes. So they can't convert correctly from micrometers or nanometers back into regular meters. So make sure you look back at those metric prefixes and that you're comfortable with those, that you can shift in and out of those units with meters. Question on this one, if there is, please ask. All right. Now before we do the next one, over on the right-hand board is a rather elegant rendering of the ultraviolet or the electromagnetic spectrum, showing the different types of what's considered light. You need to know the general order of the spectrum. Now in the book, there's a better diagram, but also in the book it gives you numbers of what wavelengths go with which type, what frequencies go with which type. That's not important. I just want you to know the order. And I'll label it in a minute as far as which end is high wavelength, which end is high frequency, which end is high energy, that sort of thing. But that's the progression of it. And some relationships in terms of light you already know, especially in regards to this end of the spectrum. Because you've got some experience with those health-wise. Health-wise, what do you know about ultraviolet light?
Sunburn.
Sunburn. And if you get enough of it, too much of it, let's say that. If you get too much over it over an extended period of time, it can cause what?
Cancer.
What kind of cancer? Skin cancer. Ultraviolet, well, let me say it this way. Visible light, your body can handle. Visible light never hurt anybody. Except vampires. But that doesn't count. But ultraviolet is higher energy than visible light. And it is a little bit higher in energy than what your cells can handle. Because it causes mutations. You get enough ultraviolet exposure, covalent bonds start breaking, electrons start bouncing around in ways that they're not supposed to, and they reform, and that's called mutation. You get enough mutation over time, that can become cancerous. But visible light won't do that to you. Your body handles visible light. But ultraviolet's a bit higher in energy, and it can cause some of those stray reactions to occur. But it's only a little bit higher in energy than visible. So if it's going to hurt you, it's going to be on the surface. It's going to be your skin. You're either going to get a sunburn or you're going to get maybe skin cancers. But it's not going to do anything to you internally because it's not high energy enough to penetrate through your body. If it hurts you, it hurts the surface. What do you know about X-rays? They penetrate, right? More specific, what do they penetrate? Skin and all of your soft tissues, right? Your muscles, your organs, everything that's not, I guess, bone. Bone is too dense. X-rays can't go through that. X-rays are higher energy than ultraviolet. X-rays can penetrate through all your softer tissues. X-rays in high amounts over a prolonged period of time, they can cause internal damage, possibly even internal cancers, because they're able to penetrate through most of your body materials, not the bone, but everything else. Then comes gamma. Gamma penetrates everything, even bone. And actually, health-wise, one of the I guess the most common sign of somebody's gotten a really high dose of radiation is what they call radiation leukemia. Because the radiation goes through the bone, it kills off the marrow. The marrow is what produces your blood cells, correct? And so if the gamma rays go through the bone and kill off the marrow, then you're not going to be making those blood cells anymore. It's called radiation leukemia, radiation-induced leukemia. Do you see that progression from visible to ultraviolet to X-ray to gamma rays? No damage to surface damage to soft tissue damage to everything damage. And that goes along with the energy of the particle and its ability to penetrate through the body. So apparently, based on what you already knew about these types of radiation, that this is the high energy end of the spectrum. And if gamma rays are the high energy end, what does that tell you about frequency? High or low? Frequency is high. Remember, there's a direct relationship. High frequency means high energy. And what about wavelengths? Short wavelength, low wavelength. So what you need to know is to be able to make comparisons. If you're asked which has the higher frequency, infrared or ultraviolet, what's it going to be? Ultraviolet, higher frequency. If you're asked which has the larger wavelength, infrared or microwaves? It'd be microwaves for wavelengths. Larger wavelength for microwaves. Those kinds of comparisons are what you need to know. Right? So know the order of things in order of wavelength, in order of frequency, in order of energy. All right, question about that? All right. Question number 2. Is giving a wavelength of 600 nanometers. I want you to calculate the energy of that. So we're going from wavelength to frequency, frequency to energy. And the wavelength is 600 nanometers. So like before, we got to shift the wavelength out of nanometers and into ordinary meters. That's 6.00 times 10 to the negative 7 meters. And then that is a number we're able to plug into the speed of light formula. That's going to calculate out for your frequency. I'm getting 5.00 times 10 to the 14th per second. That's the frequency. And I'm getting 3.32 times 10 to the negative 19 joules. Question about getting that number. At that point, we've got energy. At that point, we think we're done, but we're really not, because that's in units of joules, and the problem specifically says you need the energy in kilojoules per mole. What you've got at this point is joules for one individual photon. So we're close to done, but we're not really done, because we need to rephrase that from being based on joules to kilojoules, and from being based on one photon to being a whole mole of them. So two conversions to shift this into the right units. But at this point, we've used our speed of light formula, we've used our energy formula, we're done with the light calculations, and all that's left is unit conversions. Is there any question getting to this point? All right. Then the unit conversions. Times 10 to the third joules is a kilojoule. That's canceling out the joule units. And then for photons, there's nothing special about it being photons, but we're trying to go from one individual particle to an entire mole of them. That's going to be Avogadro's number. So 6.022 times 10 to the 23rd photons is 1 mole. And that's canceling out the photon units. So by the time you do these two conversions, you're left with units of kilojoules on top, moles on bottom. That'll be your answer. And you should get something around 200 kilojoules per mole, give or take a little for rounding. question? If there is, please ask. All right, do number 3 on your own. It's pretty much the reverse of number 2. So if you're unsure of what to do, look back at number 2. See what you get.